Our topic for today is section 10.1. It's conics and calculus. This is the beginning of chapter 10, and in chapter 10 you won't find too many things that are different from what you studied before, as I found chapter 9. But this chapter is probably the most important for your natural continuation into your Calculus 3 course. So this is really where we develop some techniques that we'll need there from the beginning of Calculus 3. So that's what gives importance to this chapter, although things are fairly simple. For example, section 10.1, conics and calculus, is basically mostly review of what you learned in your previous courses. It might be Precalculus or however it was called. So generally, what happens there, you can think of the conics in a few different ways. The name of the conics comes from the fact that you can get them while cutting cone with a plane. So if you cut it horizontally, that will be a circle. Then if you bend it a little bit like this, then it will be an ellipse. But if you bend it a lot, let me raise these two guys. If you really bend it so that it's parallel to one of the edges, then you might cut like this and never cut on the other side, so that's a parabola. And then if you bend it even more, you will cut one piece here, and then you will cut one piece here. And that will be hyperbola. But in this course, we will not connect this and make derivation of that formula and connect it too much with what happens on a cone. This is just to explain why they are called conics. We'll think about them as coming from a quadratic equation. So that will be like x squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So this is generic polynomial of two variables, quadratic polynomial. So you see, there's quadratic term, there is a mixed term, xy term, there is y squared term, there are linear terms, and there is a free constant term. So how do they influence those equations? Basically, in our course, so this part f just controls basically if your cone goes through the origin or not. Then these two guys are just for linear shift, so they don't influence the shape, they just influence where the center of the curve is. So the most interesting part is this one. And we will now discuss this middle part. We'll usually study those equations where this b is a 0. And then in our linear algebra course, we will learn how to treat those quadratic curves where this is a non-zero term. We just do some rotation. That's what they are. They are when you rotate one of the curves we discussed today, then this b term is non-zero. And then what will happen today, we'll discuss a few situations. First, we'll discuss parabolas, where one of the square terms is missing. And then we'll discuss ellipses and hyperbolas, where actually both square terms are there, and then if they have the same sign or the opposite sign. So that's generally the framework for the whole section. This is a little longer section. But let's start with parabolas. So parabolas. You will see we'll end up with one of the squares missing, but let me specify the definition. So here's the definition. The set of all points xy that are equally distant equally distant from a fixed line and a fixed point is called a parabola. And the word para here means that they are equal. So equality refers to that word parabola. And then that fixed line has a special name that's called directrix. And then that fixed point is called focus. All right, so here's the theorem. Standard form of the equation of parabola with directrix x equals negative p and focus p0. 0 p, sorry. No, it's p. No, it's misprinted in my notes. And focus p0 is, oh no, I did the vertical here, sorry. I did everything vertical here, sorry. Y equals negative p and focus 0p is x squared equals 4py. This is the vertical parabola. We'll do horizontal in a minute. So here is the equation of the parabola. So let's derive this. Why is that the equation? It's very simple. But here is the most important picture actually for parabolas, and that is you always ask yourself when you draw parabola and their graphs, you're asking yourself, where is my focus, where is my directrix? So this is the point 0p. Here is the line y equals negative p. So, so obviously, you see one point immediately, it's this one. So it's center at the origin because it's equally distant, so distance is p. And then we want to talk about an arbitrary point, let's say xy. So we will write distance formula here. We'll calculate the distance from the line, set them equal, and that's the equation. Then we'll polish it, so it's fairly simple. So what would that be? Distance formula says square root of x minus 0 squared plus y minus p squared equals, these distances, there are p points below, and this is the height y, so it's y plus p. Very simple. And then square both sides, and we'll get the equation immediately. What would that be? Square both sides. So square root disappears after squaring, so we'll get x squared. So I'm executing this foiling. Plus y squared minus 2yp plus p squared equals, when you square, now let me square this one more carefully, y plus p squared. We get x squared plus y squared minus 2yp plus p squared equals, when you square this, you get y squared plus 2yp, no product, and plus p squared. And then what happens? You cancel p squared and p squared, you cancel y squared and y squared, you get 2yp on the other side, and you get exactly what we had there, x squared equals 4py. So basically, if you have vertical parabola, then the focus is on the y-axis, directrix is on the other side, below the x-axis, and the equation is x squared equals 4py. So p is that distance, 1p up, 1p down, and that p is multiplied by 4, and that's it. And so, so this is the equation of the vertical parabola. What about the horizontal one? Then what we do is generally, and you need to just adjust the picture. Generally, I memorize mostly horizontal one because that's kind of new for us, because this one is a function. So the way it looks, I forgot to draw it. When you draw it all together, it looks like a standard like this. And then here it will be not vertical parabola, it will be horizontal parabola. So what happens? Focus is here. Now it's P0. Directrix is vertical on the left, and your parabola goes like this. I'm not sure how to do that opening. You will see in one of the problems that we'll do that will help you actually to see how big is, what is the proper way to draw that opening correctly. All right, so what would the equation be for a horizontal parabola? The same thing, just x and y change places. So it would be y squared equals 4px. So this is the horizontal parabola, this is the vertical parabola, and that's the main thing to learn today. And then of course we'll keep playing with this. So sometimes we'll do the shifts, sometimes we'll flip it on the opposite side. But generally, you don't need to memorize all of them, just do the adjustments. So for example, if you want to flip it on the left, then focus is on the left, director is on the right, there will be just a minus. So when you flip the main position. So basically memorize one of those two, switch x and y if you want to go from vertical to horizontal or the other way around. And then if you want to flip it left instead of right, down instead of up, just a minus here, and everything will be okay. P is always positive. All right, so let's see how the problems work here. So here it is. Here's problem number 16. So I erase all this, erase this. So generally when I start problem like this, I just draw a little icon to remind you what's going on. So you don't have to do it that way. My icon is this one. So even if before I read the problem, I draw a little picture. I usually like horizontal one. So here is the parabola. Where is focus? It is at P0. Where is directrix? At x equals negative P. What is the equation? Y squared equals 4px. That's what you need to know. No matter what we do, I memorize this and then I adjust it depending on the problem. So here it is, problem number 16. It says, find the vertex, focus, and everything parabola. Find the features. Features of the following: y squared plus 4y plus 8x minus 12 equals to 0. So what do we do in this problem? First thing is to complete the squares. Because obviously, since I have linear terms, then there is a shift here, so we need to recognize that shift as well. Obviously, since y squared, it will be horizontal one. So how do we complete the squares? Generally, here's the trick. Here is y squared, here is 4y. We talked about it in chapter 8. So generally, here is probably the simplest way. Take that 4 here, and then split it evenly. 2 and 2, multiply, you get 4. That's the number that needs to be added to both sides. You get the following: y squared plus 4y plus 4 equals that 4 that I added on the left, added on the right, and I get rid of ax. So 4 minus 8x plus the big one on the other side. So I want just pure square on the left like it is here. So what do I get? I get y plus 2 squared. What would this be? It's minus 8x plus 16. So what do I do here now? I will factor out negative 8. Negative 8, and in the parentheses I have x minus 2. So what is that telling me? Those numbers are telling me where the center is. So normally here, center is at 0, 0. My center is now shifted. How do I get that shift? You can use whatever you learned before. My suggestion is you will recognize where is your center when you put both of them to be 0. So x is 2 and y is negative 2. So set them equal to 0. That will tell you where your center is. So this is the center. Normally. So now my parabola will not be at 0, 0. It will be at 2 and negative 2. So here it is. Here's where my center is. So now I do the drawing the same way that I had at the origin. Now I will adjust it here. What else? I might do it differently than the book. I always take p to be positive. So p, 4p is 8. So p is 2. Okay. And what else? And I know because this number is negative, so p just tells me the opening. And this negative tells me that my parabola goes on the left. So, what would that give me? So, generally what? Let me see what happens. So, I know that it will look like this. It will go on the left. I'm not sure how much open it is. So, generally what we can do, I can put x to be 0 and solve here, if you need it. Or, I'm not too kind of picky about that part, although I'll show you the trick how to draw it. When you put x to be 0, I want to see where is the y-intercept, or two of them. So we'll get what? Y plus 2 squared is 16. So y plus 2 is plus or minus 4. So it will hit at 2 and at negative 6. So here is 1, 2. No. That the equation of that parabola, once again, it's horizontal because y was squared. It's to the left, not to the right. So my icon is to the right, but I adjusted that because p was negative. The opening was controlled by the y-intercept. And that's it. So, but I'm not done yet, sorry. I have to report where is the focus. So since P is 2, focus is where? Left or right? Always inside the parabola. So obviously focus is here, so memorizing the formula. So focus is here. So this was 2 right, so this is 0. I went to 2 left. So to get focus, go inside, which is 2 left. So this is the point. X is 0. What about directrix is 2 to the other side, so this was x equals 2, so this will be 2 more, because p is 2, so this is the line x equals 4. So here it is. Here is the directrix, x equals 4, focus is 0, negative 2, you get something else. You say find the vertex, focus, directrix, and graph parabola. Vertex is actually, I call it center because it's center of translation, but really that's called vertex. So vertex, because it is on the curve, so center is the vertex at the same time. So what is the vertex? Vertex was what we found in the very beginning, and that is 2, negative 2. Here they are. Here's our answer. All 3 features are there. As I said, I'm going to memorize too many formulas. Just memorize the main one and then do the adjustments. Let's see the next problem. All right. Here is the problem that goes in the other direction. In this one, they gave us equation and they wanted the features. Now we'll go the other way around. We'll have features and then we'll get the direction. So what would that be? So number 22 in my notes. It says find the equation of the parabola that has vertex negative 1, 2, and the focus negative 1, 0. All right. So first thing we need to decide is this horizontal or vertical? Look at our icon. The line, if it's horizontal, the line connected center and the focus is horizontal. So let me draw them and see immediately. So vertex is at negative 1 and 2. So it's negative 1 and 2. So here is the vertex, I also call it center, you notice. And then focus is at negative 1 and 0. So here is the focus. So obviously the line connecting them is vertical line. So it's vertical. Because VF is vertical. So check out the connector, C or VF. If it's vertical, it's vertical. So what is that telling me? If it's vertical, then X will be squared, and then 4P is here, and then Y. So X will be here, Y will be here. So it's vertical, X will be squared. And then what? Vertex tells you what the shift is. So X plus 1, Y minus 2. I subtract vertex, and really when I set it equal to 0, I get negative 1 and 2. And that's it. I'm done. The only thing is I need to see if I should put plus or minus here. And then also how much is P. So you see, your parabola just roughly goes from vertex around the focus. So this one obviously goes down, so it should be negative. And then the distance between focus and the center, that's your P. So that's your P. You read your P is 2. So it will be minus A times Y minus 2. Here's our question done. This was very quick. So once again, your center is at negative 1 and 2. It faces down because when V goes around F, it goes down. And then we are at P as VF. And that was it. So what happens here, we want to play a little calculus here because there's conics and calculus. So we want to talk a little bit about tangent lines. So there's nothing special here. You just calculate tangent lines the way you normally do it using derivatives. So number 83, it says the following. Find an equation of the tangent line of y equals ax squared at x equals x0. Prove that x-intercept on this tangent line is half of x0 and 0. So what are they really asking us to do? It's a vertical parabola. So they want the equation through this point. And that equation says, so if this coordinate is x0, this coordinate is x0 over 2. There's nothing really here for us to learn, more to demonstrate what we learned in calculus 1. So what are we going to do here? We want the equation of, so this is the point A. X coordinate is x0, y coordinate is not given, but if I have x coordinate and I have equation, I just plug it in. So I get ax0 squared. So I want my green line. So my green line will have which equation? Let's go point flow formula. Point flow. And that one says y minus y0 equals m times x minus x0. The general formula from Precalculus. So in this case, it would be y minus y0 is this point ax0 squared, x minus x0. Don't be afraid of so many letters. Think of x0 as 17, so it doesn't really make a difference. A is undisclosed kind of opening of parabola, so nothing big. What is m? M is actually, remember that m is the slope. So m is the slope, and that's first derivative at that point x0. So that's what the meaning of the derivative slope of the tangent line. So we'll say how much is if y equals ax squared, then y prime is 2ax. So y prime at x0 is 2ax0. That's our slope. So it's 2ax0. That's it. There's the equation of a tangent line. Looks very abstract, but actually the main thing is not to panic. So this is basically a number. This is a number. This is a number. Only x and y are variable. Everything else are the numbers. So this is the equation of a tangent line. Equation of the tangent line. So what's now our goal? Our goal is to find the x-intercept. So I'll erase this. So I want x-intercept. So just follow your knowledge. Don't panic about the way it looks. X-intercept is the point where y equals 0, because that's what it is. Height is 0. So I plug in y equals 0 and solve for x. So I get 0 minus ax0 squared is 2ax0 times x minus x0. I need to solve for this x. That's my x-intercept. And then what do I do? So if a is not 0, and it's not, if it's really a parabola, then, since 0 minus it, so I can erase the 0, then a and a cancel out. One of these x0s cancel out. So what do I get here? I get the following: minus x0 equals 2x minus 2x. Then I add 2x0s to both sides. So I get x0 equals 2x. So 1/2 x0 equals 2x. That's exactly our x-intercept. Exactly what they wanted. They said x-intercept is a what? 1/2 x0 and 0. That's it. So it was really exercise in calculus 1. Nothing really kind of fancy here or specific for this type of curve. So we just used our general principles. What is an interesting reflective property of parabolas? And for applications, this is good to learn for physics, for real life, and also to show you how interesting this topic is. What is the reflexive property of parabolas? It says the following. If you send a signal from the focus, like this, in any direction, it will reflect parallel to the axis of your parabola. What if I send at a different angle the same? This is actually, this property is being used to make parabolic mirrors or antennas. So you put your signal at the focus, and then when you send it, it goes far away. Those signals do not intersect. Of course, it goes the other way around. If you are receiving the signal, then if they are coming this way, they will all reflect. So it will go also this way. If someone sends the signal, when it reflects from the mirror, it will be collected at the receiver. So that's very important for sending the signals. And so here is the problem here. Be aware of it. So AQ1, it's a solar collector for heating water. It is constructed with a sheet of stainless steel that is formed into the shape of parabola. So solar collector, let me draw solar collector. I'm not writing text. Okay. Up to there. collector. So it's like this. The water will flow through the pipe in the focus. So here is the focus of the parabola solver. So here is that focus. So here is where water's coming. At what distance from the shape of parabola? The water, oh yes, here are the symbols. So pipe is in the focus because of the reflective property. So here is, here is information. So here is the point 3,1. So that's where it is. And they say at what distance from the vertex is the pipe. So this was given. Here is 3,1. Here is 0.30. So you know that information. So you scan like one point on that mirror, or whatever it is, reflective aluminum. So you want to see where the focus is, if that's how you build it. So what would happen here? We'll use our standard equation. There's no shift because we placed it at 0, 0. But the equation is vertical, so we need to switch it. So it's x squared equals 4py. So the only thing that's undisclosed is p, how much open it should be. And then what? Plug in 3,1. So we'll get 9 equals 4p times 1. So p from here is 9/4. And we know that that's where the focus should be at 0p. So that's where the pipe should be. Pipe should be at the focus. And that would be what? The 0 and the 9/4. That's a very simple problem, actually. Choose p so the parabola goes to a given point. This point 3,1 was given in the parabola. All right. There is one more fairly tricky problem there about constructing equation of a parabola on an undisclosed point. I'm not going to show it here. I'm going to focus on the other curves. If you if you're interested in that problem, then ask me the question, post it on the discussion, and so on. All right. Next type of curve that we'll study. So now I believe is this. Is ellipse. The set of points xy such that the sum of distances from two fixed distant point is called foci. Is constant. So that means, so what happens? Here is the center. So here center and the vertex are not the same thing like in parabolas. So center is the center of shifts. And here are the foci. Which one is F1, which one is F2, doesn't matter. So center is always in the middle of foci. That's how we place coordinate system. And here's the point xy. So left focus is minus C0. And right focus is C0. So generally focal distance is 2C. And then we want this distance plus this distance on D1. This is important for application. Generally we'll derive an equation, and when you manipulate equations, you will mostly use the ready-made equation. But this setup is important for applications. So what would that see? So we'll say d1 plus d2 is constant. And that constant is called 2a for convenience because it will appear in the equation. So that happened. Did I derive that? I did not. Okay, I'll derive quickly. So what would that be? Distance 1 is square root of what? X plus c squared plus y squared plus square root of x minus c squared plus y squared equals 2a. Then I will not ask you to do this, but I'd like you to just know how things really show up instead of just kind of having them fall from the sky. So generally we'll just polish this equation and it will start looking nicer. So quickly, just as I said, so that you see it, what happens, I'll get one of them on the other side. So square root of x plus c squared plus y squared is 2a minus b squared. And then we square both sides, so we get what? This expression, x plus c squared plus y squared is 4a squared minus 4a times square root and plus x minus c squared plus y squared. And then what happens? Y squared cancels y squared. And then when I square x plus c squared, I get the following: x squared plus 2xc plus c squared. And I'll bring this guy on the left. So it will be minus x squared. It will be minus 2xc when I bring it to the other side. It's 2x. It's just trivial algebra. Plus c squared is 4a squared minus 4a times square root. And what happens here? These guys cancel. And then, no, c squared is minus. It was plus on this side, so it's really also cancel. So I get actually 4x here. And then 4x, everybody has 4, so I'll cancel it, so I get x equals a squared minus a square root x minus c squared plus y squared. And then what do we do? We get this expression on the left, x on the right. So we get a square root of x minus c squared plus y squared equals a squared minus xc. And then if you want to square it, of course, xc has to be less than a squared. So what happens here when we square it, here's what we get. I'll rush a little bit the algebra. So this square root disappears, and I FOIL inside, so I get a squared times x squared minus 2xc plus c squared plus y squared equals square root of binomial into the 4 minus 2a squared xc plus x squared c squared. And then what happens when you distribute here, a couple of things will cancel, and we have our equation. So what would that be? We get a squared x squared minus 2a squared xc plus a squared c squared plus a squared y squared equals a to the 4th minus 2a squared xc plus x squared c squared. These two guys cancel out. That's the best rules of all. And basically we are there. That's the equation of ellipse. It still looks bad, but here's what we do. We get x squared on the left side, so we get the following. Those two are combined. And we factor out, so we get the following: a squared minus c squared x squared plus a squared y squared, which is this guy. This guy goes on the right, so we get a squared times a squared minus c squared. And here comes the main thing, that the difference a squared minus c squared gets a special name, and it's called b squared. And that's the first equation you need to memorize. That's a crucial one. So here is your b squared, and with that b squared in mind, so generally it's a good idea that we memorize this. So it says a squared. First equation here to memorize is that a squared equals b squared plus c squared, like Pythagorean theorem. And with that equation, we have the following. b squared x squared plus a squared y squared equals a squared b squared. If you divide by a squared b squared, you get the equation x squared a squared plus y squared over b squared equals to 1. And that's the equation to memorize. So we showed you what C is. So C is that distance from the focus, the foci to the center. You don't see A and B yet, but it's fairly easy to see that when I put y to be 0, you get x equals plus or minus A. When I put x to be 0, y equals plus or minus B. So they are nothing else but x and y intersects. And here is your main drawing. So here it's, of course, x-intercept is further away. So it's like this. So this is your A, this is your B, and then this is your C somewhere here. And here is your equation. So once again, the equation is x squared a squared plus y squared b squared is 1. And because of this, of course, a is greater than or equal to b. That's called horizontal ellipse. And that's the only thing to memorize. So this is, and then everything else are tricks. And by the way, what's healthy? It's healthy to see, since A is here in Pythagorean theorem, you also have a version of A here. So A is here in the intercept, but this is A as well. Why? Because if you do Pythagorean theorem, B squared plus C squared equals A squared, so A could be read there as a distance from the focus to the minor. This is major axis and this is minor axis. What about vertical ellipse? So it might be, so this is ellipse traced horizontally. What if it's traced vertically? Then the same thing. You don't need to memorize that. I always memorize this one and then do the adjustments. What would that be? So now this would be A, this would be B. A is always the longer one. So it would be then what? X squared over B squared plus Y squared over A squared equals to 1. Where is focus now? Focus is obviously here now, up and down. So here is 0 C. As I said, you don't need to memorize this is 0 negative C. You don't need to memorize them again. It's just the same thing, just readjust it, and this is your A. So this is horizontal ellipse. So it's just, this is the difference. That's it. So let's see how it all works. Let me erase this. The same story as a minute ago. Let me adjust this to save them. So first question would be number 34. We have equation and we want to read our ellipse. 16x squared plus 25y squared minus 64x plus 150y plus 279 is 0. Since I see both squares with a plus, I know that that will be ellipse. So I want to read the canonical form. I want to be able to read A, B, C, and everything. So what do we do? The same thing as a minute ago. We complete the squares. This will be slightly more complicated here because I have here 16. So what do you do when you complete squares? Factor out that numbers. It will be 16 times x squared minus 4x, and I'll leave empty space because I need to add something to complete the square. The same thing for those two. I'll pull out 25, and I'll get y squared plus 6y, and I'll leave empty space. And then I have minus 279. Then I got on the other side, I'm ready. So the same way as a minute ago, I add 4 here because it's to make complete squares, so 2 and 2 halves. You know that, I would say. I will add 9 here. Half of 6 when you square it, you get 9. Be careful, of course, on the right side, I don't add 4 and 9. They need to be distributed here, so I add 64. And I'll add 225. Is that correct? 64. Yeah. So what do I get now? This is 16 times x minus 2 squared plus 25 y plus 3 squared equals 10. Did I get 10 there as well? Yeah. And that's it. So now it starts looking much simpler, very similar to this. So when you want to read the equation of an ellipse, of course there is some shift. Main thing is to build 1 here. So divide by 10, no matter what happened on that. So we get the following: 16 over x minus 2 squared over 10 plus 25 y plus 3 squared over 10 equals to 1. But then if I want to read the equation, I cannot have anything next to x minus 2 squared. That's why I'll divide by 16 up and down, which is mathematically algebraically correct. Here I'll divide by 25. So what will that do finally? It will give me my equation. It's a tiny little ellipse. 10 over 16, I'll leave it like that. Plus y plus 3 squared. 5 equals 1. So first decision I want to make is it horizontal or vertical? It's horizontal because this number is bigger than this one. So the bigger one is called a squared. So this is your a squared. And this is, I know it's not times, so I know that's your a squared. And this is your b squared. So we'll say the following. What is the center? The center is 2, negative 3. How much is A? A square root of 10 over 4. How much is B? Square root of 10 over 5. How about C? Then we go what? C squared equals A squared minus B squared, which is, what would that be? Yeah, maybe it would be better if I just read, if I reduce them, probably. So 10 over 16 is what, 5 over 8, so I'll get 25 over 64. Minus, this is 2 over 5, would be 4 over 25. I know how much it helped me. On the top, when I cross multiply, I get what, 625 minus 256 over 64 times 25. So C is, how much would that be? On the bottom it's easy, it's 8 times 5. On top I get square root of what? 369 looks like. Yep. And is that what it is? I didn't even calculate it there. Oh, maybe I did. Yeah, so I don't know if I did correctly my calculation here. Oops, sorry, I made a big error here. I shouldn't square this. This is already squared. Sorry. So c squared is a squared. This is a square, so I shouldn't square it. I should just copy it. So 10 over 16 minus 10 over 25. So what would that be when I cross multiply? I get 90 over 16 times 25. So c is square root of 90, which is 3 root 10 over 20. So generally what, if I need to report things, so what would that be? That's a little tricky sometimes when you need to report things like your ellipse, so you have to be careful. So where are the features of that ellipse? Everything has to go from the center. So center is at 2, negative 3. 1, 2, negative 3. So here's your center. And then what? It's horizontal, so foci are left and right. So focus 1, focus 2. So I keep y, I keep the height, and I go left and right. So foci, I have what? I have 2 plus or minus 3 root 10 over 20, and then negative 3. You don't see green. What I went from here to left and right to get my 2 foci. What would be the vertices? So vertices are, where would that be? A is root 10 over 4. So vertices would be at the same shift. I mean, in the same direction, but just different one. Root 10 over 4 and negative 3. So that would be vertex 1 and vertex 2. And then on the minor vertices, now I need to shift vertically, so it would be 2, and then up and down, I would go by root 10 over 5, so it would be negative 3 plus or minus root 10 over 5. So here are those vertices, and here's the picture. So generally just keep in mind, even if the numbers are not nice, do you shift vertically or horizontally? When you shift horizontally, change your x, keep your y. When you shift vertically, keep your x and shift your y. So this was a little bit kind of body calculation of what it should be problematic. Let's go one problem where we do have features and then we want the equation like we did with parabolas. So what would that be? It says the following, number 40. Find the equation of the ellipse. If vertices are 0, 2, 4, 2, and eccentricity is eccentricity is 1/2. A couple of things to tell you if I want to give you a fair shot at this problem. Do they mean here that these are horizontal? So let me put those vertices. So 0, 2, and 4, 2. So 0, 2 is here. And 4, 2 is here. So here is vertex 1, 0, 2, vertex 2, 4, 2. So what is that telling me immediately? They call vertices, so on the ellipse, those are the vertices. Those on the major axis. The other one are just, I call them sometimes vertices on the minor axis, but they are technically not vertices. So this tells us immediately that it's horizontal. What else is it telling us? Their distance is basically 2 A's, 1 A from center, and it tells us where the center is. So center is in the middle. So where is the center? 2, 2, midpoint between 0 and 4 is 2. And also it tells us that A is 2. So you see how many things we read immediately. So here it is, I'm almost ready to write the equation. So what would that be? X minus 2 squared plus y minus, so those are shifts. Center gives you the shifts. I read A and square it here is 4. I don't know, because just B is missing. And probably I should somehow use this eccentricity. So what is eccentricity? Eccentricity is actually a ratio of C and A. So generally it tells you basically, it measures how far is your your ellipse from the circle. Because if your ellipse is the circle, your focus is at the center, and you actually, your C is 0. The bigger C is compared to A, it more, so this would be an ellipse with a very high eccentricity. C would be very close to A. So C is always less than 1, of course, because C is less than A, but the closer to 1 it is, more stretched the ellipse is. So generally what it tells us here is that it's 1/2. But we know our A because this is A squared, so C over 2 is 1/2. So from here we easily read that C is 1. So how is that helping us? Because of that Pythagorean connection, A squared equals B squared plus C squared, so we get 4 equals B squared square 1. So B squared is 3, so here's our equation. So it was a very, very simple. Actually, this is easier version than, but you need to know your main icon. So this is what I like, my icon, whenever they kind of, I don't want to memorize tons of equations like your book suggests. I memorize just this icon and those two little tiny equations, and then I do the adjustments for different direction, and so on and so on. This is a new thing, what is eccentricity? All right. One more thing. So here is example. Find the equation of a tangent line at point 3 root 2 over 2, 4 root 2 over 2 for the ellipse x squared over 9 plus y squared over 16 equals to 1. So what are we going to do here? Standard stuff. So what happens? This is a vertical one, doesn't matter, points given, one is equation. So easy exercise in Calc 1. So what would that be? Point slope. Y minus 4 root 2 over 2, my slope, x minus 3 root 2. I copy the point. The only thing I need is a slope. The real problem there is that even for my slope, I would need to solve it in terms of y. Instead of doing that, which I don't like because derivatives will be unpleasant, I'll do implicit differentiation. Remember that from Calc 1? You differentiate keeping in mind that y is a function of x, so we'll go different. Now I'll go over the notation because it's really helping us here. Equals the derivative of 1. Of course, the derivative of 1 is 0. It's a constant. Here, when you differentiate below at x squared over 9, you'll get 1/9 if you want d over dx if it was slower. Plus 1 over 16 d over dx. A squared. The derivative of x squared is just 2x, so it's 1/9 times 2x plus 1 over 16. Here comes the chain rule. Derivative of y squared is 2y dy dx equals to 0. And the crucial thing there is actually the guy that you need showed up. So what I do very often, I say here at this point, that's it, you are done with derivatives. Plug in x and y immediately so that you deal with numbers instead of with letters. This time I'm not going to follow that rule because letters are not bad, numbers are very unpleasant. So I'll keep x and y the way they are. By the way, I can divide both sides by 2 to get rid of 2's. So I'll get the following: 1/6 y dy over dx equals 1 minus 1 dx. So what will that give me? I'll get the dy over dx is minus 16x over 9y. 16 went up, y went down, and that's it. So my m, I'll get when I plug in the coordinates, it will be minus 16 times 3 root 2 over 9 times 4 root 2 over 2. I plug in the specific coordinates, and then what happens, I can cancel this 2 and this 2. I can then cancel the root 3 and root 2. And then also what else? I can cancel 3 and 9. I get just 3. I can cancel 4 and negative 16. And after all this mess, I get negative 4/3. It makes sense because it's negative. That's it. Negative 4/3. Can you leave it like this? Probably yes, because I don't like when if you polish it, then you will lose that information about the point. So that's how I would leave it. All right, so there is one more type of curves left, and that is hyperbola. Oh, but before I switch to hyperbola, just let me mention for application what's interesting for ellipse. The interesting thing is that if you have foci, so here is focus 1, here is focus 2. If you send a signal from one of the foci, then the signal reflects and hits the other one. And that's a very interesting property. And by the way, it is used at the whispering rooms. So what you do is actually, if you have elliptic shape, then someone whispers here, and the person sitting at the other focus hears that signal, while the others cannot, that are not so strategically located. And then, so for example, I noticed that that was used in some locations, like in Carlsbad, there's a restaurant, Italian restaurant, Bocca di Beppo, and they have ceilings like that. So if you sit around a longer table, bigger table, then the person that's actually strategically located can hear you while the others cannot. More famous example is the actually Central train station in Manhattan, New York, when there are actually, I forgot the name, there are some corners there where you talk to the wall, and then person sitting to the next corner can hear you while the others cannot. So tourists are lining up, making photos and all that. So it's an interesting property. All right, that was the story about the ellipse. Let's now do something about hyperbolas. The definition of hyperbola is quite similar to the definition of an ellipse. So generally we have the very similar story. So we have two foci, so here is focus 1, focus 2. So it's defined a set of all points x and y such that the difference of those two distances, so this is like point M, so difference from MF1 minus difference of MF2 by absolute value is fixed, and it's equal to 2a. And if you do the similar calculation as what we did last time when we did the ellipse, generally you will get that all these points look something like this. So the equation looks like this: x squared over a squared minus y squared over b squared equals 1. This a is the same as this a here. And generally your vertex here is, so this is 0.80, let's say vertex 2, and here is minus a0, vertex 1. Here it is. And then, but here it is. So focus T is again C0 minus C0. So they are 2C apart. And then the formula that connects A, B, and C this time, the C squared is the big one. So it's A squared plus B squared. This is what you need to know and memorize. And then shift, a couple of other tricks, but basically that's what it is. And here comes a very important part in this drawing. So let me erase this. It's important for applications. while your A is X-intercept, your B is just not visible. So there are no vertices there. But generally, they do play some role. So generally, if we draw B somewhere here, let's see. Oh, by the way, here, to contrast with ellipse, it doesn't matter who's bigger, A or B. What matters here is who's positive, who's negative. So when A is positive, we have something called horizontal hyperbola. Then you can put B and negative B, although if there are no points there, but here's what you do. You can make a little rectangle here. So here's negative B. Here is B. There's no point there. But here is where you see a C. C is basically now the long guy. So here's your C. So this is A, this is B, this is your C. Now that diagonal, because of the Pythagorean theorem, is C here. And that C is the same as this. So C is here, and the same C is here. But generally, here is the very important thing for a hyperbola. And that is the equation of the asymptotes. So what happens? You see, this is a limited curve, and actually let's go here to infinity. And generally, what is the behavior of this curve toward infinity? So when x and y are big, go to infinity, then what happens is that x squared, here's the simplest way. I'm here improvising a little bit. Minus y squared b squared is very close to 0. Why? Because x and y, a and b are fixed. So when x and y are, these are huge numbers. So they are like million and one. So they're very close to each other. So generally when you set them equal, approximately equal, actually you are getting the line that approximates your hyperbola. You can square root things and you get x over a equals plus or minus y over b, or if you solve for a y equals plus or minus b over ax. And that is the equation of the asymptote. So these are the asymptotes of hyperbola. And here is interesting, b over a is the slope of this line that has b here and a here, and actually those are exactly diagonals of your, obviously my hyperbola is not look good for the choice of this. So you're approaching your asymptote, and here the same thing, you're approaching the asymptote. You're not escaping, you're kind of straight. So these are three equations to memorize. Connection between C and B and A, the equation of hyperbola, and the equation of the asymptote. And then the same thing as before, we complete the square, then when they give us the features, then we kind of recover there. Remember, the focus is again inside, and generally things work the same way. So let me see a couple of problems. By the way, this is called horizontal hyperbola. Once again, doesn't matter is A bigger or B bigger. A is the positive one, B is the negative one. Then vertical part of hyperbola would go like this: y squared over A squared minus x squared over B squared equals to 1. So, how would that look like? Basically, it would be here in that other. Actually 2/4 of this asymptote business. So generally, how do we draw this? So generally, now y gets A, doesn't matter who's bigger once again, x gets a B, so it has, here is A, here is B, and then C is the diagonal. So here are the asymptotes, the same as before, just A and B switch the roles. And then now you draw here. So by the asymptote, touch horizontal line, here is the vertical one. And then there are tons of equations in your textbook. You don't need to memorize this equation. If this is A and this is B, obviously asymptote would be y equals plus or minus rise or run, a over b. So we'll just say equal to 0 and so on. So here are a couple of examples. All right, so let's do some similar problems like in the previous part of this section. So this is problem number 56. Equation is given, we need to recognize the features. By the way, it's obviously, whatever we do, it will contain the origin because it doesn't have a constant term. So, and it's obvious that it's hyperbola. I'm not sure horizontal or vertical, depends how we complete the squares. So I pull out 3 here, y squared minus 4y. Plus, we'll see what. And then this x squared part is a little trickier because see how it starts with a minus. So I'll pull out that minus. So we have x squared minus 6x here. It's 0. And then obviously we take half of this and square it. So we get 4 here and 12 here. Because 3 times 4 is 12. Here half of 6 is 9. When 3, when I square it, I get 9. 9 was actually subtracted because of this minus. And that's it. So now it's what? 3 times y minus 2 squared minus x minus 3 squared equals 3. So it's weird. Since I got positive number, it is vertical. When I divide, I get what? Y minus 2 squared over 1. 3 squared by 3 equals to 1. So divided by 3 here. And that's it. Now we can read everything. So it's vertical, so this is your a. So a squared is 1. So a is 1. B squared is 3. So b is 3. Your center is 3 and 2 because x is 0 and x is 3. Y is 0 and y is 2. What else? Why don't we get rid with c squared is 1 plus 3, which is 4. So c is 2. So what happens now? We repeat our main icon. The way I memorize things in the icon is what we just derived a minute ago. I memorize horizontal one. So it's here, here's your A or B, we go here, we go here. So this is your, this is A, this is B. And then I see equation of the line and everything, and then I remember c squared is a squared plus b squared. So what? Our center is 3, 2, so a little different, but then we'll do the same business. 1, 2, so here's our center. And from 3, 2, we actually build the same rectangle. What are the sides of a rectangle? Vertical one, which is a is 1, horizontal is root 3. So here is root 3. Here is root 3. I'm going to make this one smaller. Just take 7. And then it's 1 up and down. So here's 1 up and down. And here's our rectangle. Here are the asymptotes. Let me draw them in color. And here's our geometry. By the way, we promised that we'll draw through the origin, so I'm going to make this as a little hard to be accurate about it. So it goes through the origin, touches here, touches here, touches here, picture. So let's report everything. Vertices are 1 up and down, so vertices are 3, 2 plus or minus 1. So vertex 1 is 3, 1, vertex 2 is 3, 3. So this is 3, 3. Vertex 1, vertex 2. Where are the foci from center? So foci are 3, 2 plus or minus 2. So that will be focus 1 will be 3, 0. Focus minus 2, 8, 3, 4. So here they are. Focus 1 here, and focus 2 here. This one, 2. Focus 2. And what is the equation of the asymptotes? Generally, you know, if this is a root, I don't need to memorize it. If this is a root, I just draw a rectangle. So you go shift y minus, x minus, and then what is the center? Center gives you the shift y minus 2, x minus 3, and then your slope is 1 over root 3. Plus or minus. So it's all in the picture. You don't have to memorize these long formulas from your textbook. So this is how this type of problems go. Well, let's go to the other type of problems where we do have features and we want to find the equation. So here it is, number 64. It's the same thing, just we cover it backwards. So I use the same icon as there. How would that work? It says the following. Find number 64. Find the equation of hyperbola with focus 0, center 0, 0, asymptotes y equals plus or minus 3/4 x. So let's orient ourselves. So is it vertical or horizontal? So center is at 0, 0, and focus is here. So if focus is on horizontal line, it's horizontal. And what do we know? We do know that the equation looks like this: x squared over a squared minus y squared over b squared equals 1. This is c, and we know that c is 10. So generally, I don't know the sides, but it doesn't matter. So here is a, here is a b, and we know that slope of the asymptote is b over a. So b over a is 3/4, because here is the positive side. But also we know that a squared plus b squared equals c squared is 100. So we get an easy system of equations. How do we solve it? From here, b equals 3/4 of a. Where we plug it in, we get a squared plus 9 over 16. A squared is 100. So the common denominator, this is 16 over 16. So we have 25 over 16. A squared is 100. A is a positive root of this equation, because x by definition positive, so we add square root, I get 5/4, a is 10. So a is 40 over 5, which is 8. And then b is 3/4 of that, so b is 3/4 times a, that's 6 here. And that's it. So the equation is what? X squared over 64 minus y squared over 36 equals to 1. So it was even easier than the previous problem. Our next problem is similar again to a problem with ellipse, problem number 66. To find the tangent line for, and here's the equation, y squared over 4 minus x squared over 2 at point where x is 4 and y is positive. They didn't tell us what y is. Of course, you can always calculate that. We plug it into the equation. So for y, since there are two solutions, we'll pick a positive one. So we get y squared over 4 minus, what's this, 8. 4 squared is 16. 8 is 1. Squared y squared over 4 is 9. Y squared is 36. So y is plus or minus 6, but we pick a positive 1 because of this condition. So here it is, point A is 4 and 6. And then what? Then we know that the equation is y minus 6 is x minus 4. That's point slope formula to get shift. The only thing missing is the slope. So to get slope, what do? We take our equation and differentiate implicitly. So what would that be? D over dx of y squared over 4. And, maybe I should multiply by 4 actually. Yeah. That doesn't matter, but if I multiply by 4, I get y squared minus 2x squared is 4. Makes it cleaner. So d over dx of y squared minus 2 over dx over x squared is 0. Derivative of 4 is 0. Here y is a function of x, so it will be 2y minus 4x equals to 0. And here I'm not going to solve for dy over dx. I'll plug in because I need only the slope for my particular point. So this will be what? 2 times, how much is my y? 6. How much is my slope? I call it m. Minus 4 times 4 equals to 0. Now I solve for my m. And that would be 16 over 12, which is 4/3. I read it here, and I'm done. So here is the table point. Y minus 6 is 4/3 times x minus 4. As I said, you can leave it like this. And one more very nice problem. Actually, it's a very neat application, one of the nicest applications that we show in our curriculum, and that is it is connected with the way how GPS is actually system see you. It's an interesting application of mathematics. So let's say the following. We have two stations, F1 and F2, that are 300 miles apart. So this one is just negative 150, 0, and 150. That's our choice of coordinate system, so that they are apart. And then there is a boat that actually sends a signal to both of them. And then there is a difference in signal in the response because this distance is, or they are sending a signal at the same time to the boat, and boat catches a time difference in receiving, and that time difference is 0.01 second. So delta t is 1,000th of a second. And then boat travels keeping that distance the same. Where will the boat hit the coast? So here's the coast, boat is here, here are the stations. The boat will go somehow and hit the coast somewhere here. So what is this? Generally, this difference in time comes from difference in distances. So difference in distances is difference in times speed of the signal, which is speed of light. This is the electromagnetic signal. So that would be 0.001 times 186,000 miles per second. So that will give us a miles. So 186 miles. So generally what happens, if it keeps the time difference, it will also keep the distance so that MF1 minus MF2 will be all the time 186. But then we know that that means it travels along hyperbola, and on that hyperbola, if you remember in derivation, this is 2a. So that means that actually it will move on hyperbola and a horizontal hyperbola, and a will be 93. And then what? But we still don't know that hyperbola if we don't know particular point. And let's say that that point is yes. So what would happen? yes, they gave us that point where it is, is X, they don't tell us what it is, and 75. So generally what happens is in that hyperbola, we know that C is 150, and we know that A is 93. So from the equations that C squared is A squared plus B squared, when we solve it, we get that B is approximately 170.7. So here is the equation of the motion, x squared over 93 squared minus y squared over 107.7 squared equals to 1. This is the equation of the motion. And then what? Actually we do know where will it hit the coast, and that will be where it will be age 93, so it's 93 is here. And then obviously it will be 57 miles from the second station. And then just one more thing, where is that boat currently if we know a y coordinate? So if y is 75, then when we plug in 75 in this equation and solve for x, we get that x is approximately 110.3 miles. So here it is. We know now where is the boat exactly if he wants to use this time difference, and we also know where will it hit the coast. So that's an interesting, nice application. As I said, GPS do this with just more stations and a little more complex geometry of those differences.